Ionic compounds form when metals transfer electrons to nonmetals, producing oppositely charged ions that attract strongly. In this module, we'll use sodium chloride, magnesium oxide, and calcium chloride to strengthen electron dot structures and ICSE style reasoning. The central idea in ionic compound formation is electron transfer. Metals usually have one, two, or three valence electrons, so they often become stable by losing electrons. After losing electrons, a metal has more protons than electrons, so it forms a positively charged ion, called a cation. Nonmetals often need one or a few electrons to complete their outer shell. When a nonmetal gains electrons, it has more electrons than protons, so it forms a negatively charged ion, called an anion. Sodium and chlorine show this clearly. Sodium transfers one electron to chlorine. Sodium becomes Na+, and chlorine becomes Cl-. These opposite charges attract each other strongly, and that electrostatic attraction is the ionic bond. Now turn that idea into a clear bonding sequence. A metal atom, such as sodium, loses its outer electron and becomes a positive ion. A nonmetal atom, such as chlorine, gains that electron and becomes a negative ion. After the transfer, both particles have more stable outer electron arrangements, often an octet, or in smaller atoms, a duplet. The important point is that the electrons are not shared. Ionic bonding is the attraction between the ions formed after electron transfer. So the sequence is: electron transfer creates ions, and electrostatic attraction holds those ions together. Use sodium chloride as the model for a complete ionic bonding answer. First, write the electronic configurations. Sodium is 281 and chlorine is 287. Sodium has one electron in its outermost shell, so it loses that electron and becomes Na+. Chlorine needs one electron to complete its octet, so it gains that electron and becomes Cl-. Show the transfer clearly. The electron moves from sodium to chlorine. It is not shared. After transfer, both ions have stable outer shells. Because Na plus and Cl minus have equal and opposite charges, they attract strongly by electrostatic force. One sodium ion balances one chloride ion, so the formula is NaCl in a 1:1 ratio. Electron dot structures focus only on valence electrons because these are the electrons involved in bonding. Magnesium has two valence electrons, and oxygen needs two more electrons to complete its outer shell. So magnesium transfers both of its outer electrons to oxygen. Magnesium loses two negative charges and becomes mg2+. Oxygen gains two negative charges and becomes O2-. In a dot structure, the transferred electrons are shown using dots or crosses. The final ions are then written in brackets, with their charges outside. The formula mg shows that one magnesium ion balances one oxide ion, giving a neutral ionic compound overall. Calcium chloride uses the same ionic bonding idea, but the electron transfer is split between two chlorine atoms. Calcium has two electrons in its outer shell, so it becomes stable by losing both of them. This forms a calcium ion, Ca2+. Each chlorine atom needs only one electron to complete its outer shell. So one calcium atom transfers one electron to each of two chlorine atoms. Each chlorine becomes a chloride ion, Cl-. Now the charges balance. One Ca2 plus is matched by two Cl- ions. The total positive charge is +2 and the total negative charge is -2. The neutral compound is written CaCl2. Calcium chloride also shows why ionic formulas are based on charge balance, not simply on one atom joining one atom. Calcium forms Ca squared, while each chlorine forms Cl. One chloride ion balances only one part of calcium's 2 plus charge. So calcium needs two chloride ions. Together, the two negative charges add up to -2, which cancels the +2 charge on calcium. That gives the formula CaCl. The small 2 belongs only to chlorine, meaning there are two chloride ions for every one calcium ion. When writing ionic formulas, match the total positive charge with the total negative charge, then use the simplest whole number ratio. Here is a useful comparison. In calcium chloride, calcium loses two electrons, but each electron goes to a different chlorine atom. That gives one Ca2 plus ion and two separate Cl minus ions. So the formula is CaCl. In dot structure form, it is shown as Ca squared Cl Cl. Magnesium oxide is different. Magnesium also loses two electrons, but oxygen needs both of them. So the ratio is one magnesium ion to one oxide ion, giving milligram O or milligram squared O squared. In both examples, the same rule controls the formula. Total positive charge must balance total negative charge. To wrap up, ionic compounds form when electrons move from metals to nonmetals. The metal becomes a positive ion, and the nonmetal becomes a negative ion. Sodium chloride is a one-to-one example. Magnesium oxide shows a two-electron transfer between one metal atom and one nonmetal atom. Calcium chloride shows why two chloride ions are needed to balance one calcium ion. The key rule is charge balance. Total positive charge must equal total negative charge. Next, we will connect ionic structure to the physical properties of ionic compounds.